All right, silly people, here's the situation. Uh, we have an electron um, with spin L equals 2. It's a spin 1/2 particle with J angular momentum equal to 5 halves and M equals to 5 halves. And we're going to try and find the Clebsch-Gordon coefficients for the cases where J is also 3 halves and M is also 3 halves and all the combinations therein. Um, so the first one's actually not too bad, and it's going to be the basis for the rest of the problem. If we have a quantum state like this, it's going to be L 1/2. So it's LSJ, so 2 1/2, 5 halves, and then to the M 5 halves. Um, so because J and M are already in their maximum values for um, this system, this is going to be exactly equal to the state vector, um, where I'm going to use L, ML, um, S, and MS for my basis. And that, so again, it's exactly equal to the state vector in this case, where L is going to be 2, ML is going to be also 2, S is going to be 1/2, um, and MS is going to be 1/2. The the highest state possible for the system. Okay, that's the first one down. Now, if we look at, we'll look at now M is equal to 3 halves for this same case. Um, to do this one, you want to use ladder operators. Um, that is, if you use J1 plus or minus I J2 times any quantum state psi Jm, that will be equal to h bar square root j plus 1 minus m squared minus or plus m under a radical times quantum state j m plus or minus 1. Um, if we choose 5 halves for our m, and we are looking for the lowering operators to take it to m equals 3 halves, then we're going to have j1 minus I j2. This is going to be j, it's going to be LSJ, so 2 1/2, 5 halves, 5 halves, um, will be equal to h bar square root. J is still 5 halves, so it's going to be 5 halves times 5 halves plus 1. M is 5 halves, so we're going to do 25 over 4 minus, this will be plus 5 halves. And then over here we'll end up with the m equals 3 halves stuff. So we'll have 5 halves there, 3 halves there. Right. Um, when you subtract the ladder operators like that, what you end up with is L minus and S minus. The L and S ladder operators, respectively, um, where we're now just operating. We've already proved that that state has the state vector 2, 2, 1/2, 1/2. And on the right hand side, we'll just go ahead and start simplifying that radicand. We'll have 25 over 4 plus 5 halves minus 25 over 4 plus 5 halves. So those 25 over 4 guys will cancel out. I don't know why I didn't write this quantum state all the way out to 1/2, 5/2, 2 1/2, 5/2, 3/2. Okay. Um, moving right along. So if we use the definition of a ladder operating L minus operating on a state vector L ML SMS, it will be h bar times the square root of L plus ML times L minus ML plus 1. Okay. That multiplied by the same state but with the ML reduced by 1. So it'll be 1, 1/2, 1/2. Right? Okay. So then also S minus has a similar operation. It'll be h bar times root. We'll have S plus MS, S minus MS plus 1 under a radical times now the same state, but with, I'm going to write the general formula here. It's L ML minus 1 S MS. And this one, it's L ML S MS minus 1. Okay. Fantastic. So let's plug that into our stuff. So we'll have, for the L operator, under the radical, we'll have a 2 plus 2 times a 2 minus 2 plus 1 term. That'll be times 2, 1, 1/2, 1/2. And then we'll have for the S operator, we'll have 1/2 plus 1/2, 1/2 minus 1/2 plus 1. And then we'll have 2, 2, 1/2 minus 1/2. On the right hand side, I'm going to go ahead and simplify that radical further. So it'll be root 10 halves times h bar times the state that we're looking for. Notice that all of the radicals just have factors of h bar on them, which means you can get rid of those. All right. Evaluating the left-hand side. 2 plus 2 is 4, so it's going to be 2 times 2, 1, 1/2, 1/2. 1/2 plus 1/2 is 1, so it's just going to be 2, 2, 1/2 minus 1/2. On the other side, it's root 5 of this state. Then if we move the root 5 to the other side, we have the final form of the basis vectors for this state. 2, 1, 1/2, 1/2, 1 over root 5, 2, 2, 1/2, half minus 1 half. Now we have to do the same thing, but with j is equal to 3 halves. But because, excuse me, because we're going to have the same ms, we'll be able to use the same state vectors, actually, the same basis vectors. J is now 3 halves, m is going to be equal to 3 halves. Since we're going to be using the same basis vectors, and we know that when we reduce j to 3 halves, that it'll be orthogonal to when it was 5 halves, we can use that to solve for the new Klebs-Gordon coefficients. So all I'm trying to say is that the state 2, 1 half, 5 half, 3 half, you take the dot product of that with 2, 1 half, 3 half, 3 half, that's going to be equal to 0. So then when you do that, you're literally just going 1 over root 5. It's 2, 2, 1, 1 half, 1 half, plus 2, 2, 1 half, minus 1 half, dotted with some constant alpha over there, times 2, 1, 1 half, 1 half, plus some constant beta, 2, 2, 1 half, minus 1 half, equals 0. Doing that dot product, it's just 2 alpha over root 5 plus beta over root 5 is equal to 0. So you're just finding that alpha is equal to minus beta over 2. If you also take advantage of the normalization of the basis vectors, you can actually get something like that and solve for beta, which is, we have 5 beta squared over 4 is equal to 1, so beta equals root 4 over 5, which is 2 over root 5, which means alpha is going to be minus 1 over root 5. So that when we construct this state, it will look like it's going to be minus 1 over root 5 to 1, 1 half, 1 half, plus 2 over root 5 to 2, 1 half, minus 1 half. The problem also asks you to just list off the Klebs-Gordon coefficients. Klebs-Gordon coefficients being just CLS of JM semicolon MLMS for each of these guys. We found all of these already. It's for, and all of them have the same L and S. It's all 2 and 1 half. We started with 5 halves, 5 halves, and then ML was 2, and MS was 1/2. Yeah, that was just 1. That was the first one we did. Then we did 5/2, 3/2. Um, to We ended up with one of them being 2 1/2s. Nope, we ended up with one of them being 1 1/2, and yet we ended up with one of them being 2 -1/2. Um, for the 1 1/2, we had 2/5. For the 2 -1/2, we had 1/5. Um, then the last two that we did uh, was 3/2, 3/2. Uh, we had a 1/1/2 one, and we also had a a 2 -1/2 one. The 2 -1/2 one ended up just being 2/5 again, but this one was -1/5.